You don't have
it's okay.
some pocket for this.
So that,
Do you have some pocket with this?
no, actually, so I can
Okay.
hold it. It's okay.
Okay.
What is it?
Okay. Okay. Our next and the last speaker of this session is Ayse Borat from Bursa Technical University, who will have a talk on contiguity distance. Please.
Thank you very much, and thank you very much for giving me opportunity to have a talk in here. Today I will talk about contiguity distance, and this is a joint work with my colleagues Mehmetcik, Pamuk from Middle East Technical University and Tane Vergili from Karadeniz Technical University. And here is the plan of my talk. First of all, I will introduce the homotopic distance and speak about why it is important. And then I will introduce some combinatorial stuff. Then I will focus on contiguity distance, and later on I will discuss the relation between contiguity distance and simplicial Schneemann category and discrete topological complexity. And then I will talk about the relation between contiguity distance and the geometric realization. And moreover, I will say something about barycentric subdivision. So first of all, what is a homotopic distance? This definition is due to Macias-Virgos and Mosquera-Lois. So we start with two continuous maps, and we say that homotopic distance between these maps is the least integer k if we can find an open covering of X with k plus 1 subsets, such that the restriction of F and G on UI is homotopic for each R. And before I start to introduce the importance of homotopic distance, I want to recall some basic definitions. One of them is due to Michael Farber, and this is called topological complexity. So let's start with a path fibration. Pi from the path space of X to X cross X, which takes a path and maps it in its initial and final point. Then we say that the topological complexity of X is the least integer k, such that we can find k plus 1 open subsets which covers k x times x, such that we can find a section of pi on each UI. And another definition is the definition of the Schneemann category, and it is as follows. We say that the Schneemann category, or simply category, is the least integer k if there exists an open covering of X with these k plus 1 open subsets, such that each inclusion iota is non-homotopic. And homotopic distance actually is a concept which generalizes these two concepts. I mean, if we take the projection maps as given in here, then we say that the homotopic distance between these projection maps is just the homotopic the topological complexity of the space. And we can also say that if we consider the identity map and the constant map, then the homotopic distance between these two maps is just the category of the space. Well, this is quite obvious, but which is not that much obvious is that if we consider these inclusions, which are given with these formulas, then the homotopic distance between these inclusions is just the Schneemann category of the space. So now we know that homotopic distance generalizes these two concepts, topological complexity and Schneemann category. And one other thing is We know that homotopic distance deal with maps, but on the other hand, topological complexity and Steinig-Schneemann category deal with not maps, but spaces. This gives us the opportunity to play with composition of maps. Well, I'm talking about the homotopic distance now, and it is likely to prove some open problems in topological complexity by using composition properties of homotopic distance. What is at the background is the following three theorems, which tell how homotopic distance behaves under composition. Well, I want to introduce these theorems, and they are all due to Macias-Virgos and Mosquera-Lois. One of them is the following: if we are given two maps, F and G, and another map which is composable with F and G from the right-hand side, then we say that the homotopic distance of these compositions is less than the original homotopic distance of F and G. And as an example, I want to illustrate an alternative proof of category is less than or equal to topological complexity. So let's start with the Steinig-Schneemann category. From a few slides back, we know that it is just the homotopic distance between the identity map and the constant map. And if we play with the functions in a very careful way, then we can see that the identity map can be written with as a composition of projection and inclusion maps. And also we can say that the constant map can also be written as a composition of these two guys here. And now we apply the theorem 1, and we obtain that this thing is less than equal to the homotopic distance between projections, and this is exactly the topological complexity of the space. So it's just one my proof. And let me introduce the other two theorems. One of them is as follows. We have two maps, F and G, and this time we have another map which is composable with F and G from the left-hand side. Then we say that the homotopic distance between these compositions is less than the homotopic distance of F and G. And the third theorem, which looks a bit more complicated, tells that we have H and H dash from Z to X, and we have two other maps from X to Y. Let's name them F and G. We want this relation to be hold. So we say that this inequality holds. And there's one other theorem about homotopic distance, which is in the sense, well, actually, this is a theorem which says that homotopic distance is homotopy invariant in some sense. Well, we say that X and X dash are of the same homotopy type, and similarly, we say the same thing for Y and Y dash. And moreover, we say that there is a homotopic equivalence beta and another homotopic equivalence alpha. And we say that this diagram, the following diagram, is commutative in the sense of being homotopic, and this other diagram is also homotopic in the sense of being homotopic. Then we say that the homotopic distance between F and G is the same thing as homotopic distance between F dash and G dash. Now let me talk about some combinatorial stuff. First of all, I want to start with being contiguous. So let's start with two simplicial maps. We say that these simplicial maps phi and psi are continuous if a simplex in the domain, let's say sigma, we have then, if we consider the union of phi sigma and psi sigma, then this will constitute a simplex in L. And if we take another two simplicial maps again, we say that they are C contiguous if we can find a sequence of maps HIs such that H0 is phi and HC is psi, and each pair, each such pairs is contiguous. And moreover, we say that phi and psi are said to be in the same contiguity class if we can find an integer C such that phi and psi are C contiguous. Now I want to talk about elementary collapse and elementary strong collapses. First of all, let's start with a simplicial complex K. Then we say that let's pick two simplices. One is, let me illustrate it on this example. This is our K, the simplicial complex, and let's take this simplex and name it as tau, and we consider a face of that simplex and name it sigma. But sigma is not an arbitrary face of tau. Actually, sigma must have no other cofaces. Then we delete sigma and tau, and we get a simplicial complex, and we call this procedure elementary collapse of K. And this is the elementary collapse of K. And if we consider the inverse of the elementary collapse, then this is called the elementary expansion. And let me move to another definition. Strong elementary strong collapse. But in order to understand it, I need to define the definition. I have to give the definition of what it is to be dominated by a vertex. So again, I want to illustrate it on that example. Let's say that this is the simplicial complex K. Then we say that a vertex V is dominated by another vertex V dash if every maximized simplex that contains V also contains V dash. For instance, in here, we have two simplices which contains V, the first one and the second one, and we can see that they also contain V dash. But on the other hand, we can say that V is not dominated by V, because if we consider this simplex here, then which contains V dash, but we can easily see that it does not contain V. Now let's focus on elementary strong collapse. An elementary strong collapse consists of removing the open star of a dominated vertex V from a simplicial complex K. So I consider the same simplicial complex as before, and we know that V is dominated by V dash, and we consider the open star of V, these dark parts, and we remove it from K, and we obtain this simplicial complex on the right hand side, and we call this an elementary strong collapse. and the inverse is called elementary strong expansion. And a finite sequence of elementary strong collapses or expansions is called a strong collapse or strong expansion. And we say that two simplicial complexes have the same strong homotopic type, which is usually denoted by this, if they are related by a sequence of strong collapses or expansions, and also being in the same homotopic type is related to contiguity. So we can give such a definition. We start with a simplicial map phi from K to K dash, and we say that it's a strong, it is a strong equivalence if we can find another simplicial map psi from K dash to K such that these two are held. So we say that K and K dash are in the same strong homotopic type, have the same strong homotopic type, if and only if we can find a strong equivalence between them. And another definition is we say that a simplicial complex is strongly collapsible if K and the singleton complex are of the same strong homotopic type. Now let's focus our main concept, the contiguity distance. This concept is due to Macias-Virgos and Mosquera-Lois. In their paper about homotopic distance, they introduce contiguity distance, they give the definition, and they leave it as a feature study. Now we start with, actually, contiguity distance is kind of a distance between simplicial maps. So we start with two simplicial maps, phi and psi from K to L, and we say that the contiguity distance between these simplicial maps is a least integer K if we can find subcomplexes J0, J1 up to Jk covering K, such that if we consider the restrictions of pi and psi on Ji's, then they are in the same contiguity class. And my colleagues, Pamuk and Vergili and myself, introduced some propositions. First of all, is very obvious. It doesn't really matter if we consider the contiguity distance between phi and psi or psi and phi. And secondly, we introduced the following. The distance between two simplicial maps, let's say phi and psi, is equal to 0 if and only if these two maps are in the same contiguity class. And the last one is contiguity distance is well defined on the set of equivalence classes of simplicial maps. Now we have the following theorem, which is actually the simplicial analog of the theorem that I introduced before. This time we have K and K dash to have the same strong homotopic type. In other words, we can find a beta, a strong equivalence between them. And moreover, we have L and L dash have the same strong homotopic type. So we can find a strong equivalence type between them. And we say that this diagram is commutative in the sense of being in the same contiguity class, and also this other diagram is also commutative in the sense of being in the same contiguity class. In other words, these are fault. Then we say that the contiguity distance between phi and psi is the same thing as the contiguity distance between phi dash and psi dash. Well, the idea of the proof is the following. Since that we have strong equivalences, now we can use that proposition, which tells that if we have two simplicial maps and if we have at least a right strong equivalence beta, then this is holds. And also we have another proposition which can be understood as the left strong equivalence analog of the previous proposition. In other words, if we have two simplicial maps and a left strong equivalence alpha, then these two are equivalent, are equal. And the first proposition is due to that proposition, and the second one is due to that proposition. And then we conclude that we have we can prove the theorem that we introduced. And moreover, I want you to notice that the result of the above theorem is still valid if one takes beta to be not a strong equivalence, but just right strong equivalence, and also alpha to be not a strong equivalence, but just left strong equivalence, then the theorem is still valid. And let me introduce the relation between conjugate distance and simplicial Standing-Schnellmann category and discrete topological complexity. Well, we expect to have such a relation because we know that there is a relation between homotopic distance and the Standing-Schnellmann category and the topological complexity. So before I introduce the relations, let me introduce the definitions of simplicial category and discrete topological complexity. First of all, let me introduce the simplicial category. But in order to understand this definition, we need to understand what is a categorical simplex, subcomplex, sorry. Well, these definitions are all due to Fernandez-Ternero, Macias-Virgos, and Mosquera-Lois. So let me introduce categorical subcomplex first. So we start with a simplicial complex K, and we consider a subcomplex of K, and we say that this subcomplex is categorical if we can find a vertex of K such that this inclusion and the constant map at the vertex V0 are in the same contiguity class. And moreover, we say that simplicial LS category of a complex K is the least integer n such that K is covered by n+1 categorical subcomplexes. And one easy to see fact is K is strongly collapsible if and only if simplicial category is equal to 0. And let me first give a characterization of simplicial category in terms of contiguity distance. As expected, we have that the contiguity distance between the identity simplicial map and the constant map at the vertex V0 is just the simplicial category of K. And secondly, if we consider these inclusions, which are also simplicial maps, then we have that the contiguity distance between these inclusions is just the simplicial Standing-Schnellmann category. And one other theorem tells that suppose we have phi and psi as simplicial maps from K to K dash, then if K or K dash is strongly collapsible, then we say that the contiguity distance between these two maps are 0. And for the converse of the theorem, we can say that the contiguity distance between pi and psi is equal to 0 for any pairs of maps from K to K, then K must be strongly collapsible. Now let me introduce the discrete topological complexity, but in order to define it, I need to introduce the fiber subcomplexes. So let me start with a simplicial complex K and a subcomplex omega of the categorical product of K is called fiber subcomplex if we can find sigma from omega to K, a simplicial map such that these two maps are in the same contiguity, are in the same contiguity class. By the way, delta is the diagonal map as given in here. Now let's focus on the definition of discrete topological complexity. We say that discrete topological complexity of a complex K is the least integer n such that K square is covered by n plus 1 fiber subcomplexes. And we have such a theorem. Well, the following theorem is first mentioned in Macias-Virgos and Mosquera-Lois paper, which is about the homotopic distance of maps. But they didn't give a proof. So in our paper, our archive paper by my colleagues Pamuk and Vergili and I, we give an explicit proof. So it is as follows. If we consider the projection maps to the first and the second vectors, then the contiguity distance between these projection maps is exactly the same thing as the discrete topological complexity of a complex. And next, I want to focus on the relation between contiguity distance of any simplicial maps and simplicial Lusternik-Schnellmann category and discrete topological complexity of their domain and codomain. So if we are given two simplicial maps, phi and psi from K to K dash, then we can see that the contiguity distance between these two guys is less than or equal to the simplicial category of K of the domain. And if we are given any simplicial maps, phi and psi from K to K dash, then the contiguity distance between these two maps is less than or equal to the discrete topological complexity of the codomain K dash. And let me talk about some geometric realization related things. We introduced the following theorem. If we have two maps, phi and psi, then there is a relation between the homotopic distance of their geometric realizations and the contiguity distance of these simplicial maps as follows. And we also introduced an example for the strict case of that inequality. So we considered a simplicial complex K as given in Pamuk and Minias paper. And by Fernandez, Ternero, Macias-Virgos and Mosquera-Lois, it is already proved that the simplicial category of that complex is equal to 1, which makes its contiguity distance between the identity map and the constant map is equal to 1 as well. On the other hand, K is, if we consider the geometric realization of K, then it is just a contractible space. So this makes this homotopic distance to be equal to 0. So we get the following. This is just equal to 0, which is strictly less than the conjugate distance, which is 1. And now let me talk about barycentric subdivision. First of all, let me introduce what is an induced map of a simplicial map on the barycentric subdivisions. So if we have a simplicial map, phi from k to k dash, then the induced map on the barycentric subdivisions, which is defined as follows, is a simplicial map. And a theorem by my colleagues and me tells that conjugate distance between the induced maps on barycentric subdivisions must be equal than less than or equal to the conjugate distance of the original simplicial maps. So as a corollary, we can see that simplicial category of barycentric subdivision of K is less than or equal to the simplicial category of K. Well, this is already proved by Fernandez, Ternero, Macias-Virgos, and Mosquera-Lois in their paper as a consequence of some finite space related theorems. And also in another paper by Fernandez, Ternero, Macias-Virgos, Minos, and Mosquera-Lois, they give a direct proof for that corollary. And here we gave much easier proof, and we only use the contiguity distance. So we consider phi to be the identity map, the simplicial map on K, and we take psi as the constant simplicial map, and we put them in that theorem. So let me start with this guy, the simplicial cat of the barycentric subdivision of K. And since that we know that this is just the identity map and this is a constant map, we can write, and also from the definition of simplicial category and its relation with contiguity distance, we can write this equality. And from the above theorem, we can write this inequality, and we know that this is just the simplicial category of the complex K. And that's it. That is, these are the references. This is our archive paper and other references that we use for this work. And thank you.
Thank you very much for the talk. The usual, customary. Any questions, comments?
You were mentioning that you want to use homotopic distance to prove new stuff about the complexity or contiguity distances. Do you have something in mind that you think is particularly useful?
In the open problems, well, we tried something on what was that? Something the simplicial analog for cohomology things because of these whites, but we couldn't end up in some clear results. So I don't know, maybe in future.
Any more questions? Comments? If not, then thank to the speaker again.
Okay, so just an announcement, we should have the lunch very soon, and the bus, for those of you who are going to the it's in 1:30. So my suggestion is, those of you who are going for the excursion, please, kind of group together and stay on walk over there, you will ask that you are served first, so that you can eat before you go. All right. Yeah, that's it. Let's turn the speaker again.
Yeah.